here. Okay, hi everyone. We are looking at chemistry functionality for upcoming versions of Wolfram language. And, wow, okay, seems like we have a bunch of, let's see, where are we starting here? Atom labels, is that where we're starting?
Right.
So this is the analog of vertex labels.
Right, and it definitely uses a lot of the same machinery as vertex labels under the hood, except it goes a step further. And if you just vertex labels doesn't really try and find a position for the label that doesn't conflict with the lines drawn, and so we go a step extra to try to do that here.
But you're not succeeding in that case.
Oh no, so the first is an example of what if I just use the placement straight from graph plot. But then,
okay, but so to me, this is very interesting functionality for graph plot too. Has somebody fed this back to Charles and that team?
no, I do need to get in touch with them for a few things.
No. That's not what I'm talking about. If you've got a way to actually label a graph that has the labels not, I mean, maybe it's specific to chemical graphs, which are planar. Well, they're not necessarily planar, but the chemical graphs have. What special features do chemical graphs have with respect to this labeling?
I mean, they're already so laid out that often there is a place. In a regular graph, it's not obvious to exist one.
I mean, so with a chemical graph, you definitely generally want things to be like 120 degrees with a few exceptions. Here, you specifically want to look and see if there's a charge, and if so, you avoid the after right position, or let's see, after above, that type of thing. I mean, the main thing holding that back, though, would be that the compiled code that iterates over the edges and isn't in the kernel, it's in C++ and accessed via library link. So it could be used. I could write a wrapper function.
But I'm not. The implementation is not the important part. The important part is this a useful layout capability for ordinary graphs? And if we should determine if the answer is yes.
Only for a subset of possible graphs that are.
I understand, but the same. But that's true for. Oh, don't do this to me. Okay, whatever.
So I'll send an email to the discrete math group about the labeling.
Okay,
position.
fine. All right. Okay. Anyway, so this is okay. I mean, by the way, I think that's too far away.
Yes.
And what are we doing? I mean, how are we are we doing a graphic design review, or how are we determining answers to questions like that?
So after this meeting, I was going to contact design and ask them about the appropriate size for the fonts and the appropriate default style.
But I think some of these are sort of too far away, and this one looks like, this is like, well, that one might be like, tritium or something.
Agreed. As you know, it's tricky. But figuring out how big your label is and then moving off from there. But I do. But yeah, I'm always trying to improve it.
Well, right. But I mean, there's ways in graph with placed, for example. Placed has a way of. I mean, I assume that you will support in atom labels the same thing that vertex labels supports, which is the big list of put this label at this position, right? Put
yes.
this. Okay, but so if you do that, placed has special purpose. Placed is capable of having special purpose tags in it for different kinds of situations. So you could have something which is a very chemistry oriented placed. Do you see what I'm saying?
I do. Right. So one example there of something that isn't supported in graph, but would be useful here would be placed with subscript as the second option.
Sounds good to me. Yeah, I mean, right. So you can.
Yeah, I mean, in general, it's actually using. So graph supports so many different placed specifications that I went in and I'm using the same functions they do, so as to.
Okay, fine. Oh, I see. You already. Okay, so great. So you've already got a bunch of these.
Yeah,
Okay.
and so between now and the code freeze is when I have to make what do you call it? The bond labels work as well.
Okay, so wait a minute. So this is a so you've got atom labels, and then you would have and then you have bond labels also.
Right, but so currently bond labels will just place them directly on the center of the bond, which is what GraphPlot does, but it's not what we want to do. And so we need to, and placed above and right don't work currently in Graph.
What's the analog of highlight graph for a chemical?
There isn't one. So you would just call, molecule plot and give a pattern as the second argument, and it highlights some part.
Okay. That's right, because these are molecule plot outputs, which are graphics, not graph objects.
Correct.
So I have a question. I mean, if I take that molecule and I say graph of that molecule, do I get a graph right now? Because it'd be really nice if I did.
No, I believe you have to call molecule graph.
What do you mean molecule graph? Here?
Right.
I didn't even know there was a molecule graph, but okay. Why isn't it just graph of that molecule? Why doesn't that just work?
I have mentioned this to Charles.
It's not up to Charles, really, is it? Is it an up value thing?
So I could make an up value.
Right. So I think you should agree with Charles how you're going to do it, because I think it's a desirable thing to have. Now, if I say vertexless, why did this not preserve? I think that this should preserve the molecule graph should preserve. That's really crummy. I mean, I think it should preserve the coordinates. Why not? Why not give it molecule plot coordinates in the graph here?
So that is a good point. I don't know. It does it. Let's see. So it brings over any annotations that are intrinsic to the molecule, but it doesn't bring over the coordinates. So if you ask for the annotation rules of that, or I guess options is how you access. So all of the identity of the atoms and bonds are listed as annotations in that.
Is that the way that they're okay? I mean, I don't know if that's the best way to do that. And like a double bond, is it indicated with two? No, it doesn't seem to be indicated with two. What's it, right? Why isn't that a double edge there?
Because it's let's see. So the edge has an annotation of bond type goes to double.
Okay, so
that would seem wrong to me.
Okay, all right, fine.
There might be a method option, but I don't have it.
Okay, but I feel strongly that that graph of molecule should just work and should preserve the coordinates.
And how far do you want to go back if you assume have done this and then you make molecule of percent?
I don't think that has to work. I mean,
okay,
it'd be nice
just
if it
make sure.
It would be nice if something like that worked, but I don't know. I mean,
well, so
is it plausible that could work?
Because of the annotations, it generally does.
Okay, well, fine. If it can work, it can work. But if it doesn't have annotations, what are you going to do?
We did discuss this a while ago. So it assumes carbon. I think,
yeah, and hydrogen's hanging off where they need to hang off. But what if there's a valence 5 node?
Right. So that becomes the point where options would be useful. Like if there was a graph molecule function that had options, which were automatic valence rules or valence replacement rules.
Yeah, right. That seems like not a bad idea, but I think that, and at the first instance, molecule of graph could do the obvious thing and just give an error when it doesn't work.
I believe it. I mean, so to the most part, I believe it should at the moment. But I mean, if you gave it something like complete graph 5, it might puke.
What would work? So if I take molecule of this.
Yeah. Oh.
Splaffaroo.
Okay. Well.
Okay, it should work. Yeah, okay. But it's really important that you preserve the coordinates here, I think.
Okay, yeah.
Okay, let's keep going here. Lovely.
And so, so the one specification that's really unique to molecules here and not in graph is that you can put the atom index. You can use so instead of the quote atom index there, you could use molecule property of formal charge or any particular atom based property.
Where are you showing that?
So if we go down, yeah, that one.
What does molecule property? Wait a minute. So this is. Wait a second. That's a function, isn't it? Molecule property. That
it's a wrapper. I mean, it's inert. Yeah. It's just a representation of the property. In retrospect, I might not have created that symbol, but it is so molecule property of a molecule, like of the string, then applied to a molecule or a list of molecules returns the value.
Well, it's the same thing as entity property.
It is modeled after that, yeah, but it only needs one argument because it's
always about a molecule.
Right. But in this case, it allows me to find any instance on the right-hand side within the atom labels of molecule property, and then go in, grab those values, and resubstitute them in.
Such a shame we don't have muonic chemistry and hyperon chemistry and all that kind of stuff. Then we would have to have a new. Never mind. I'm just kind of joking. But
just keep going. We will get there.
Right. We've got other things.
We need to go in both. I mean, I'm thinking in bigger directions generally, like with crystal structures or with macromolecules, but we could also get smaller.
Or metals.
Yes. Ethan on our live stream is saying there should be machine learning for molecules. Maybe we can say something about what's happening with that.
Right. So so I need to schedule a meeting with you. I have a function that needs reviewed for generating features.
Okay.
Yep.
That is what we need for doing machine learning of, I don't know, this whatever it's called, quantitative QSAR type stuff. Is that right?
Right. So that's one of the machine learning with molecules is not nearly as mature, and it doesn't produce as many amazing results as with images. But so people are still really trying to figure out ways of featureizing the molecule, and every paper comes up has their own, and they're not.
Yeah. Well, look, the primary point is that image processing, image stuff is basically you're trying to act like a human. In doing these things with molecules, there isn't any human in the loop. So there's no guarantee, insofar as neural nets vaguely do something similar to brains, it's sort of therefore unsurprising that image processing is something you can do with them. It is by no means self-evident that you can do things with molecules with them. It seems to be the case, but it is much less self-evident, so to speak. And
I think a lot of it depends on, do you choose some kind of featureizer that is that captures the chemistry that you're looking for?
Right.
Yep.
When we were doing this sort of stuff, when I was in the pharmaceutical industry, we would choose our features that would be appropriate for the problem we were working on.
Yes.
As well as the particular metric, the similarity measure, and the distance measure.
Right.
Right. So next week, I'd like to show you basically a function called molecule features, which acts as an operator. It is a function that takes parameters and when applied to a molecule or a list of molecules, returns the numeric array, the relevant numeric array.
All right. So let me just understand what you're doing here. So this is atom labels. What is this? This is
so atom
index. You're saying atomic number is, atom index would be one thing you could give as a value of atom labels. That means put the atom index as the atom label. This is saying put the atomic number of the atom as the atom label, correct?
Yes.
Okay. And it's kind of nice that there's a molecule property wrapper here that at least is optionally available, because that allows you to say, I mean, if I happen to want to write the word atomic number as the label of an atom, I'm toast at this point. Oh, no, because atom labels could be a list of atom labels, or rather, presumably, atom list. Okay, given a molecule, let's get very basic here. Given a molecule, oh, this isn't a molecule. Oh, I wish this was just a molecule. I wish I could pick this up and just put it somewhere. Why can't I do that?
So if I could find the bandwidth to do so, or just the time away from the other projects that I want to do, I would love for molecule to format as a graph does, and to give you a nice raft when you click on it.
Okay, fine. All right. So that's something we need to put in the project list, basically, as a thing to make happen. Okay, so atom list is a list of atoms. And so what I would be able to say then, oh, that's a little confusing, because if I have a graph, right, then its vertex list, then I can map over the vertex list to say what to do for every particular, right, given a name of a vertex, I can say what its label should be. That won't work here. Unless I want to say every carbon atom, I mean, can I do that in saying atom labels goes to atom of C goes to blah, blah, blah? Like
Yes.
every carbon atom gets a this.
Yes, and and other patterns too. You could do formal charge goes to greater than 0 to get positively charged atoms.
Okay. All right. I mean, this seems uncontroversial. This molecule property thing, that seems fine. Okay. Multiple labels. Oh my gosh,
and so this is also some. I mean, this is an extension of what graph plot.
Oh my gosh. Well, that's something GraphPlot might like to have too.
So so they do. So you can specify. So that example with the B and the D, like above and below, that is taken directly from vertex labels.
Really? That works in vertex labels? Who knew?
Yes.
Okay. Okay, fine.
I didn't know actually until I went to set it up. And when I saw how much work there, that's when I knew I had to piggyback off of their work rather than try and.
Yes. Okay, what is this? What is this? I'm sorry, what is this?
Wait, which one are we?
This one, sorry, this one here.
Oh, I mean, so that one is a little silly. Let's see. So any atom with an atomic number greater than 6 gets labeled by.
I can see what I mean. I can read the code. I'm just asking what the semantics of what's going on here is.
Right. So that atom is a pattern, and it matches certain elements in there, and then the other one, the underscore.
Wait. Mm-hmm. How can it match? That isn't a pattern. I mean, this is a pattern. How is this a pattern?
So it's a pattern as accepted by molecule substructure, fine molecule substructure, molecule plot.
Oh wow!
So or you could think it's a query atom, I guess, but it describes. I think of it as a pattern, but it is not a Wolfram language pattern.
Okay.
Because I mean, in general,
this is
Wolfram
pretty
language
weird.
patterns don't have a method for describing patterns in a graph, or at least I did. This was the best I could think of when we.
What are you talking about? Wait a minute. Yes, graph rewriting is complicated. That's what our whole physics project has, provided lots of both tools and conceptual technology for. And we are about to talk about chemical reactions as graph rewriting. But we'll come to that. I mean, look, in the end, absolutely, we're going to want to specify things with molecules as, molecule transformations are graph rewriting. But I don't think this is graph rewriting. This is just a vertex condition. Right? Yes, this is not a graph. This is not a condition on a graph. This is simply a condition on, I mean, even I don't know whether you even have a valence. For example, if I wanted to say all atoms with valence larger than 2 or something, can I do that
I believe so.
with some other one of these wacky properties? Is that right?
So, I mean, I believe either valence or atom valence. I would.
Okay, but fine. But so these are local properties of. I mean, I think this is a little weird, but I mean, I understand why it's desirable to have these kind of. Oh, gosh.
But
See,
right,
the reason this is problematic is that the official pattern for this would be, what is the atom? It will be atom of whatever its element, whatever the element is, and then it would say, slash semicolon,
atomic number of elements greater.
well, it would be more like molecule property of, atomic number, and that whole thing of LM, greater than 6. That will be the more official pattern way to write it.
But then you run into troubles because some of those would be like valence, and valence is not a property of the atom; it's a property of the atom.
I realize. I understand that. I understand that. So it's a mess, and that the valence case is a case where you do have to admit that this is embedded within a graph. Look, I consider this fairly hacky, but I think it's still useful, and it's probably a decent shorthand, which there's no reason to attack. Michael, do you have any particular comment on this?
I agree, and similar to the discussion that we had a couple of years ago for entity property and related things, yeah.
Yes.
When and how to refer to the thing with condition. I agree it's not 100%, but I think it's useful and natural.
Yeah. All right. Okay. Fine. Okay. Chemical formula. What is this?
That's probably the most useful one for beginning people.
So we do get a lot of we have a way to represent the just an unspecified chemical form or a specified chemical formula without reference to a molecule in alpha, and it allows us to answer a lot of questions. And so this is the bringing.
So yeah,
basically, so this is basically smiles to formula. Is that right?
No, smiles really has the whole bonding. Here we typically don't have the bonding. We just know what's inside.
Right. We in the end we just know the element tally, and that's enough to answer a lot of questions.
I see what you're saying. So this is just the textual version of that formula.
Mm-hmm.
But I don't understand. If I want to enter
no, not quite. Like normally what we see in a textbook is a chemical formula, and there are multiple molecules that might match.
Absolutely.
Yeah.
And no, what I'm saying is, how do you enter chemical? I mean, to me, there's a chemical formula here, which is, apart from the factorization of this piece here, is just it could be an association that just contains element names and counts. Correct?
Right. And I mean,
that would be underspecifying. Like in this case, there's a little bit more than just the tally because of the subscript 3.
So you can look at the expression tree of that.
There's a touch more than the summary.
Okay, well, explain chemical formulas to me for a second. Okay, so when this business about factoring groups of atoms, the two operations in a chemical formula are, as I understand it, the multiplicity of the atoms here and the multiplicity of collections of atoms. Is that correct?
Yes.
Yes. There is also some bonding implied. So for example, that chlorine is bonded to the bismuth and the thing in parentheses is also bonded to it. It's not specified, but it's implied.
Right, but we don't have a way to, at the moment, what do you call it, to go from the formula to the structure. There would be special cases where we could do that, but we haven't coded those up or anything.
Okay, so hold on a second. So I don't really understand the notation of chemical formulas as such. I mean, what you have here is something where there's a shorthand input, which is this just this string. But what is the full structure of chemical formula?
So I mean, it's not something it's let's see. So it is just a grouping with a list of you know. So H5 is. I mean,
No,
it's
I'm not
just
sure that's the
grouping
right
we were
thing.
just
I mean,
talking
so
about. Right.
so okay. So if I just say this. Okay, so my question is this the right representation? It seems like a very weird representation to me.
So I'm not. Let's see. I only chose it out of convenience. That I'm not.
Okay, what really is a chemical formula? What is the grammar of chemical formulas?
Let's see. So I think it's similar. It's what we're seeing here, but you could imagine it being a hierarchical structure. That there would be, instead of, so I use list here, but you could replace list with chemical formula all the way down, basically, except for this idea of something being multiplied by a number. And so in alpha,
yeah, I get it. So look, it's a bit like trees.
Mm-hmm.
Well, except for this multiplicity concept. Let me ask you again. I'm sorry. And there was this comment about bonds, and I didn't quite understand that. In what sense is this formula? I mean, if I say H2O, and if I said OH2, are those like just conventionally different, or do they mean something slightly different?
Oh, those are technically the same, but we write it as H2O because of conventions that chemists usually accept.
Okay, so you know, if I were to enter that string in a different order or something, or you know what order you want, like I say CH something or other rather than HC something or other. So you have an implicit set of orderings for the atoms. Is that true?
Yes. There are rules on that from the IUPAC.
Hill ordering is one particular example.
Okay, but so what is the encoding of bonds then?
Well, so for that particular formula there, from looking at that, you can tell that bismuth is central, and that there are three phenyl groups coming off of it, and then 2 chlorines coming off of the central bismuth.
How do you know that? I'm sorry.
Just
so what's that? What happens if
written? I think.
Okay, it's convention. That's what chemists do.
Okay,
I mean,
let's say the thing was
use
3-armed. Okay, let's say that wasn't bismuth. I don't know. Pick a random rare earth with valence 5 or something. Okay, and so it has 5 arms coming off it. How would you write that string?
So I tend not to write the structural formulas. I just go for the Hill formula where everything is written in orders.
There are limitations to this pseudo-hierarchical, pseudo-structural variation on a linear notation. There are shortcomings. And when there are shortcomings, generally they don't try to represent 5 separate attachments. They'll just resort to the Hill formula.
What is the Hill formula?
Carbon first, then hydrogen, and then alphabetically the remaining atoms.
With no atoms included more than once.
Okay, so it's just an inventory. It's the thing that we were talking about before.
Correct.
Essentially just an association of counts.
Basically.
Yes.
Okay. So again, I'm coming back to this again. What is the, okay, so the order matters here. And so, for example, could this be, whatever it is, C6H53BI, and then C2H whatever 7 or something on the other side? I could repeat the carbons in different places here. Is that correct?
So yes, I mean, as I've written it, like this object does not, it doesn't normalize. It doesn't really even check. You could enter things in generally any order.
So that's a valid kind of thing, correct?
Yes, but I imagine when you go to look for a molecule that matches it, you might not find one.
Find one.
No, I
And the
realize that. I
matching
mean,
is
that's-
purely done on the element counts on the Hill formulas.
Okay. Let's let me loop around this again. I'm trying to understand. Okay, people are going to machine generate the innards of a chemical formula. We need to have some internal representation that isn't, that isn't completely silly in terms of how that looks, because this seems pretty arbitrary to me. This does not seem readily machine generatable. Because it's got all kinds of, naked atoms here and, all kinds of weird stuff.
But if you machine generate, wouldn't you not machine generate a molecule rather than a formula? And throw the vast majority of information
Possibly.
away?
Yes, but well, okay, but you might want a formula. Let's say you're doing stoichiometry or something, and all you care about is the formula.
Yep.
Wouldn't it be nice to be able to get, from this thing, to be able to derive what you need for stoichiometry with an easy piece of code, rather than having to go and, deriving that for this is a mess, isn't it?
So I use that because it maintains the hierarchical structure, and it
No,
I think
I
it's
get
pretty
it.
faithful.
but it allows you to faithfully represent the stuff that they come in. If I were to programmatically generate them, then I might just enter in. So it should eat an association, like as a first argument. Carbon goes to 3, hydrogen goes to this, and that would be the easiest way to.
Which is a Hill formula-like thing, from what you're describing.
Right.
Correct.
Okay. But so getting out of chemical formula, getting out that association also seems like a desirable thing to be able to do.
And
maybe that's what you have here.
Yeah.
I see. Element counts is that what you're saying?
Yeah.
Okay.
A large fraction of basically, especially in the Wolfram alpha area of usage, of people put in chemical formulas rather than molecules.
And that's troublesome when they do control equals, when we have, let's see, in alpha, when the number of isomers is far larger than we're going to offer as alternatives, as did you means, then we just parse to the formula. In that case, there is no Wolfram language representation, and so the control equals does not always work.
It.
And there are still many things that can be answered, like masses and other things.
All right, again, I'm going to push this one more time. Can anybody think of any other underlying representation of this chemical formula that is perhaps a bit more principled than this?
So I can take that to the drawing board. So if we agree that this is a useful function and the ins and outs work, I can consult others on the.
Okay, but maybe we should just brainstorm for a second more about this.
Multi-tree?
Yeah, I was wondering about that. But
But don't we have
we've
such
just
a
got
thing?
trees. No, we don't have such a thing.
Multi-tree, is that a forest, or is that?
No, a forest is a set of trees.
Okay.
Technically.
Well, okay. So even just doing something that involves, C arrow 6, would that be better? Or is that not any better?
I feel like that's actually less consistent, because like in the earlier one, the H5, the comma 5 is consistent with the comma 3, which is out. And this one I feel like looks a little bit unusual to me.
And are you happy with with this one here, with the 1? Are you happy with not having that canonicalize to BI, 1? How do you write a parser?
I agree. The canonicalization could be comma 1, but not in the display.
No, obviously.
I agree.
But
this
so
would
what's
be
the
more
parser
consistent.
here? The parser just says everything is a pair, and everything's a pair, and it either has a list as its first element or presumably an entity. Okay, fine. I think that I'm okay with that. I think that's parsable at least.
I agree. The comma 1 that makes it more consistent.
Fine.
Okay.
Okay. Now let's talk about the blue background, which I don't really buy.
Right. Will absolutely, after your input, I was definitely planning to go to design on it. One thing I like entity formatting, type formatting for this. One thing that I like that entity does is when it breaks out into, goes from being an output cell to an input cell, it tells you now that it's an entity, but I don't have that working here.
What do you mean it tells you it's an entity?
Well, so if you take an entity, like if you go into that output
The
cell,
type gets added.
I thought.
So too.
No.
Sometimes it does.
The font weight changes.
Yeah.
Hmm.
I didn't think it added anything.
Right.
But okay, so the question is, what do we have? What is the graphical the graphical indication of a molecule? I mean, it's just a summary box right now, but it says molecule. I don't know that I think I would not go with some kind of blue, yet another color type thing. I mean, especially since there's a formula right there.
Mm-hmm.
I would go with some kind of flat gray box like this, rather than a bordered thing, given that you are used to seeing formulas there. And then maybe, go ahead.
Well, should it have a head like with hard brackets when it formats? Is chemical formula of this gray box?
I don't think it should. No, not for output.
Okay.
Conceivably, I don't think it should. And I think when you say master, that's really kind of whatever. I mean, if that's useful to say that, fine, but it should also say it's a chemical formula before it starts telling you it's mass. Okay. Let's see, we have all kinds of comments on our live stream, which I haven't had a chance to look at here. There's comments about canonicalization of chemical formulas, of which there is none, basically. It's what you type in is what you get.
Right, and then you can ask for the Hill formula and you get back an object with head chemical formula with them in the most canonical order that we know.
Okay. Okay. But then I could take this, presumably, and I could feed that to chemical formula, and it would give me a Hill formula, chemical formula. Is that right?
Yes, that is what it will do after
okay,
the meeting.
We'll do soon. Okay. All right. And then if I say molecule of, so if I say, for example, chemical formula, about the only one I know, let's do, I'm so embarrassed about these.
Just do CH4, I tend to go for just for the.
I'm going to do that just for fun. And now I say molecule of that. Is that even a thing? Yeah.
So that's where I don't know. I mean, just a priori, you can't know. You could make a molecule of disconnected atoms, but that's usually not what people would want.
Okay, what isn't that a real thing? Isn't that calcium carbonate, or am I totally confused? This one I know is a real molecule.
Okay. So right. So if you
go a little bit down, I think some of what you want to do comes just a couple lines down.
So you can ask for its entity list, and that would be all of the entities in the knowledge base that have the same formula. Or you can you can look to outside sources for isomers.
Sigh. I mean, that's terribly complicated. For cases like H2O, where we know there's a single, I mean, okay, question.
That does sound reasonable. I mean, it's, well, so it, yeah.
How often will there only be one isomer? Or is it only for totally trivial molecules that'll be one isomer? And as soon as you get beyond that, it'll be like tons of them.
Yeah, for organics, it's common to have multiple isomers. It gets combinatorially explosive real quick.
Okay, but is there an obvious canonical molecule to return from a chemical formula?
For some of them, there definitely would be.
Yeah,
water.
With diatomics and some triatomics, all the single atomic cations and neutral species, obviously. But once you're into the triatomics, it gets problematic quickly.
I mean, so molecule doesn't tend to call interpreter, but molecule could do that. It could, to find just one, it could call interpreter on the formula. And if it receives back an entity, then return that.
But I feel like there would be so many times disappointing that you might want not to do it for the few cases where it can be uniquely done.
I don't know. People are going to want to do this. They're going to want to take the formula and say, give me a molecule based on that formula.
That's an open problem in computational chemistry, period.
What?
Doing just what you said.
What
Well,
about random instant 2-argument form?
What? That's crazy, Michael. I mean, it's entertaining. A crazy, you pick a random isomer. That's what you're saying.
Exactly.
No, that's crazy. I mean, it's entertaining, but
I mean, also in general, like, so if we're calling the knowledge base, we basically we get all of the entities in the list, and then we pick a random one from it. The same with PubChem, or we're looking at an external library that can generate them.
Okay, so that one, I mean, give me an example where there's more than one. If I say C10,
H14, or
okay,
H6 actually, then
spin. What's it doing? My gosh,
right?
what
so
is
I believe
it doing? It's gone bonkers. What is it doing? That was extremely unsavory.
So the Wolfram alpha parse is to formula molecule of that, and one of the pods is all of the isomers that we have, and so that's part of the purpose here, is to return a good result in that case.
Okay, you were defining some cases where it is a slam dunk to get the molecule from the formula,
right? And those might be the cases where interpreter of chemical of that just returns one thing.
Well, I understand that. But so one thing we could do is at least molecule of chemical formula for those slam dunk cases would work, and for the other cases it would say multiple isomers use blah blah blah. That seem reasonable? Least allows molecule of chemical formula H2O to work.
And I mean, for it could be fast too. We could just keep a what do you call it? A little hash table in the Packlet.
Okay.
The easy ones.
Right. So comments here about people asking about AlphaFold and language, and yes, things like that are hopefully coming. That is a different meeting about biosequences. We're only dealing with ordinary molecules here. There was an earlier question about hemoglobin and the representation of how do we represent a thing like that, where there's a, I don't even know what you guys call that. I mean, where there's an atom just hanging out in a cage in a molecule. What is that called? What is that? You know what I'm talking about? You have a protein and it has some random, like vitamin B12 or something has cobalt or something sitting in it.
A metal complex, if you will.
That's what it's called? Okay.
Yeah, overall, it's called a complex. I don't recall what the metal atom would be if it has a special name.
Okay, but do we have a way of representing something like that?
Not yet. We've been talking about some additional bond types so that we can handle that, and that atom would then be anchored to the coordinating heteroatoms with the lone pairs on them, but no formal bonds.
What does that mean? I mean, so because right now we have a graph that represents where things have bonds. What do we do? Okay, naive question. What do we do for ionic, molecule type things?
We don't draw a bond.
Like? What's that?
We don't draw a bond. So NaCl is just Na space Cl with the appropriate plus and minuses superscripted.
Right. It's a couple of disconnected graphs.
I see. So it's graph. Is that what would happen with this metal complex things as well, or not?
Not necessarily.
It depends if you have coordinates. I mean, that's when. So if you import the thing with coordinates, then you can.
But doesn't NaCl have coordinates as well?
Not generally. I mean, you'll find NaCl in a crystal structure.
Yes.
Yeah.
And that is another thing that we need a different representation besides molecule for.
Okay, naive question. I mean, are there bigger ionically bonded molecules?
Yeah, something like
Sure.
sodium sulfate. The sulfate has got covalent bonds between the sulfur and the oxygen, but between the sodium and the sulfate ion, it's an ionic bond,
Okay,
as it were.
but generally in things which we consider to be individual molecules, there's typically only one ionic bond, or there can be a molecule that's made of zillions of ionic bonds and not a crystal, so to speak.
Well, not a zillion, but a handful would not be unreasonable. You know, the
Example?
sodium sulfate, for example, there are 2 sodium atoms involved.
Well,
So there would be 2 ionic bonds, as it were.
I see.
But
And
sodium
if-
sulfate, though, it comes in a crystal structure, though, generally, right?
Yes.
I mean, it's not,
Yes.
molecule wouldn't be the best way to represent sodium sulfate.
Well, it depends. It depends on the application.
Right. But I'm just, for 3D plotting, for instance.
Okay,
Yeah, no,
naive
if you want-
question, guys. When this is so naive, I'm really embarrassed, but you dissolve salt in water, right?
Mhm.
NaCl
Yes.
in water. Do the NAs and the Cls hang out near each other? Or do they
No,
sort of-
they're hydrated by water molecules.
Okay.
They have a
Yeah.
shell of water molecules around them.
And they can
Oh,
actually
each-
direct
so-
up to 2 layers of shells of waters.
Yes.
Okay, so in other words, they really don't hang out together.
Not anymore. No.
No, the closest you'd get would be in the gas phase.
It would be even confusing, Stephen, as Bob just said. You can make NaCl a single molecule. It has a very shallow binding, but it's a purely covalent binding. It's no longer an ionic binding as
Oh.
a single molecule.
Mhm.
Oh, and that's what in the gas phase, is that what's happening?
If they get close enough together, that would be the
Yeah.
case. Yeah. If you put sodium, if you put salt, for example, in a mass spectrometer.
But otherwise, the standard thing is a crystal. I mean, with the ionic bond, you would expect you get lots of NaCl's all in a crystal structure.
Yep.
That's kind of the idea.
Generally, yep.
And so we've,
Okay.
and so Bob and myself also, we've been working on Wolfram language representations of that.
Yeah, that
apart
came from
all-
last summer's summer school project.
Right. Okay. And is that what's that going to be roughly? I mean, is it going to be crystal structure of blah, blah, blah?
I think we were calling it crystal the last time we looked at the code, but it's been a while since I've worked on it, and Claudio's been busy with other stuff.
Okay. But I mean, but there's a crystal which is an abstract crystal, and it's a crystal with actual sodiums and chlorines in it, and so on.
Yep.
Okay. And then what's the interface between the chemistry? Oh boy, this is getting complicated. I mean, then we have to deal with things like surfaces and so on, presumably.
Is sort of, yeah. There's no direct connection right now. We've been working on something for the function repository that we give the basic pieces to import a CIF file and then be able to render it and then expand the crystal lattice in various directions by
Right.
so many unit cells and so on.
So the CIF has a single unit cell in it, or the CIF has multiple unit cells?
It's the unit cell. Generally, they're a bit expanded so that they have whole molecules instead of fractional molecules. But it has all the symmetry transformations encoded in it.
I see.
So the whole lattice can be generated from the information in it, and that's what we do.
Interesting. Okay. Okay. All right. Let's talk about what on earth is this G thing? What is that G thing?
Oh, so that specifies that it's in the gas phase.
Oh gosh.
So again,
Ah,
something that is very useful when writing out chemical reactions.
Jason, is that subscripted? It shouldn't be.
It's yes, yeah.
Yeah, that's an oops.
No, you're definitely going to be in the loop on the formatting.
wait a second. You're saying it shouldn't be a subscript.
No, it should be immediately following the end of the formula.
Okay. Why don't we do it in a different color or a different gray level or something?
Yeah, that sounds good.
Yeah, that would be nice.
I mean, I believe that's probably similar to how we do it in alpha.
Okay. But now, in terms of the underlying data structure here, I assume it's gone. Where is it? The gas evaporated or something.
Oh, right. So So let's see. So right now it appears in an annotation rules option because I didn't know where to put it in that structure.
Well, what other kinds of annotations can there be?
Charge or phase.
And how do you do charge for an ion in a molecule? How are you specifying charge?
So in a molecule, the charges have to go on the atoms themselves.
And
so
that's
then,
done by doing what? Atom and then formal charge arrow blah?
Yeah.
And so here, this is for the whole molecule. That's
Correct.
okay. Well, so what's the most analogous thing to what we're doing with atoms and other molecules in terms of these annotations?
So,
I mean, do we use annotation rules for something else or not?
No, and so actually, so right now, if you look at the usage, my plan was the input form of that right now would have it in an annotation rules option, but I don't think that's the correct thing to do. I think if the usage that I printed above that I has a second argument, so it would get put into a second argument being the charge.
Well, that makes sense. That seems fine. That seems fine. I mean, you should be able to have something more beautiful than I would have thought a paren gas or something in very small letters would be a nice way to do that, and less obscure. Unless that's such a common usage that.
Yeah, well, so we'll consult with let's see, I almost said comic books, no, textbooks, but actually Jason is very familiar with the IUPAC's standards on this, and so that's where we'll
Okay, all right, fine. Okay, great. All right, onward here.
So having so just quickly, if we have a chemical formula, then it becomes very useful to know whether it matches a given molecule, which is why
I see.
We have this.
Well, what about molecule match Q of molecule? Wait a minute. What is molecule equivalent Q?
So that was the introduced in 12.0 to tell if two molecules match each other, basically.
As in match in what sense? That their bond pattern is the same.
Let's see. Yeah. So if you find an isomorphism and you rearrange the atoms in molecule 2 to be in molecule 1, then they would be the same molecule.
So it's the analog of graph isomorphism for molecules.
Right.
Is it in fact graph isomorphism, or is there some kind of weird chiral thing going on?
So they need to be isomorphic. They need to have the same stereochemistry and the same atom types and bond types.
Okay.
I mean,
so there is more stuff than a graph because there's stereochemistry.
Mm-hmm.
Okay.
But currently we have no way of, if given a molecule pattern, you can tell whether a molecule it contains it. So if you had a molecule of octane and a molecule pattern of 4 carbons bonded together, then molecule contains Q would give you yes, this contains that. But there's no way of looking at a pattern and saying, does this represent molecule? Right. So you could have a pattern that was 8 carbons together and the actual molecule octane, and because the molecule contains the pattern and the pattern matches every single heavy atom on there, we would say that they match.
Well, yeah. So you're saying here, molecule is just a straight molecule with isomorphism, and chemical formula, I understand what that is. Does this, and this molecule pattern, does that mean this molecule pattern represents some version of the whole molecule or some subpart of the molecule?
It represents the whole molecule aside from heavy atoms or aside from hydrogens. I mean, the pattern could include hydrogens, but doesn't necessarily need to.
I get it.
Yeah, a pattern can be a part of a molecule, it can be an exact molecule, or it could be a family of molecules that are related based on the pattern.
But if it's part of a molecule, molecule match Q will only match if the thing on the left-hand side, the first argument, is just that fragment, right? It's not a molecule contains Q.
Right.
Yeah.
Okay, fine. Looks good to me.
So those are in red because they're not merged into this branch and they don't work yet. All right.
Okay. The variety of comments on our live stream here, which I want to just look at. Various things about graph neural networks. Yes. Graph neural networks. Yeah, I mean, we're working on graph neural networks. It's coming. It's coming. Comments about biochemistry. Lots of machine learning models exist. I don't know whether we've got ones in the neural net repository yet for biochemistry. Do we?
I don't think so, but yes, there are some out.
That might be an interesting. I mean, who's going to be responsible for those? Is it going to be the chemistry team or the machine learning team?
Machine learning team.
Whoever's not in the meeting.
Do
So
they
to me,
know
in
that?
general, I mean, it comes down to like, I mean, how do you featureize it? And then once you know how you featureize it, then how do you build your nets around to work with those features? And so to me, that means a cooperation between teams.
Okay, so maybe
Exactly, of course.
maybe there needs to be a discussion with, I don't know. So Citra, I think, is the person dealing with the neural net repository these days.
There's some discussion with the machine learning team with Julio. He has an intern who wants to do something like this. We want to see what's come out of this. But generally, it cannot be the chemistry team because the chemistry team is not much involved with machine learning. As I said,
But the machine learning team is not much involved with chemistry.
Right,
Yes.
well, I mean,
Yes.
so
We can advise. We can advise.
well, so there. I mean, so yeah. So I think the molecule stuff is becoming mature enough that it can meet the machine learning.
I mean,
Previously, it was a little early.
in the latest version, we have the features, but we already have some kind of.
Maybe there is still the reaction to be done, which is a non-trivial subject, and we have 20 minutes.
And so let's see. And so one thing we're sliding by here, I have some options there for molecule match queue that I feel
They
like
looked reasonable to me.
Okay.
I don't exactly know what resonance that's this case here, right? Of whether to care about that order.
Exactly.
With resonance or resonance structure?
So in this, I mean, it's here you would, so it's up to you guys whether it would be include resonance structure, but I feel like resonance is just the concept of delocalized bonds being in resonance with each other. And so
look, include stereochemistry is whether to take account of stereochemistry.
Yes.
Include resonance. Does that mean whether to take account of resonance, as in to cause this thing to be the same as the one with its double bonds in the opposite place?
Exactly. Yes.
That seems reasonable to me.
Okay.
Let's see. There's a comments from Richard on our live stream about self-referencing embedded strings, selfies. Anybody know about this?
Oh yeah, no, I definitely. Let's see. Yeah, so I would like to write an encoder for that in Wolfram language. So it's like smiles, but it's useful in machine learning because so you can't just break up a smiles chunk into little pieces and learn anything useful from it because you've got all these pieces that depend far back into the
okay,
string.
I get it. Right, it's context dependent, whereas this is some kind of context independent. That sounds interesting.
Yeah, there's a Python implementation that I would like to study and then.
Fair enough.
Yeah.
Okay. The machine learning part and the net encoder stuff will be a separate meeting next week, hopefully.
Okay. All right. Chemical reactions.
Right. So we've been thinking about this for a long time, and I keep thinking that that there are two different distinct use cases that exist, and so that's why I keep thinking of it as two different objects. So one of them, so the chemical reaction represents a single, an actual instance of a reaction where you have actual chemicals combining and making products.
That's what a normal person thinks of, the non-chemist.
A comment from Richard here that every selfie string is a valid chemical. That's interesting and non-trivial. Not obvious how that could possibly be true. But okay, so it's a representation of graphs that has, well, interesting. Okay. All right, I'm sorry.
So that's what I remember. It allowed you to tokenize the string and then rearrange it in chunks and come up with a valid molecule where you couldn't do that with smiles.
Yes.
Jason, please send me a reference on that.
Will do.
Thank you.
Yeah, send it to me too.
Yep. So here, again, I went for the same formatting as above, and am open to suggestions there.
Okay, hold on. I'm trying to understand this even basically. I mean, to me, we were just talking about this in a different discussion. You know, chemical reactions are like graph rewriting.
Not quite. It is exactly this distinction between this first one and the template above.
Okay. All right. So, okay, let's just get some basic things. So there's sort of formula level representations of reactions, and there are presumably structure level representations of reactions. Is that a true statement, or is that a bad distinction?
I think it's orthogonal. There's the graph-based one, which is the templates, and then there is the second example here that Jason has, which is an exact reaction that you would use in the laboratory to make something. I think that's more of the practical distinction between the two.
What is an exact reaction versus a? I didn't understand.
So, in other words, you would have, instead of just saying an esterification reaction with some carboxylic acid and some alcohol, you would have the reaction for esterifying benzoic acid with isopropanol.
Basically, it's the difference between having particular molecules that you're reacting versus generic templated molecules that you don't necessarily care about what's attached.
And virtually all named reactions of the persons are of this type of that are generic.
Right. So, so what I wrote was a generic alkene dimerization. You can write as a pattern. And I'm not familiar enough with what graph rewriting means to say if it's equivalent or not. But it's a structural transformation where you have mappings between the vertices on the left and the right, versus just an instance of that when it's after it's been applied to a set of molecules.
Okay, so there's a whole literature and a whole set of people who've been doing sort of graph rewriting to represent molecules, and that sort of world has intersected with the world of stuff we're doing in the physics project, and that world also intersects with category theory and a whole bunch of other sort of pieces. And it feels like that approach is a very nice, clean, general approach to this kind of thing, and one that we should be kind of trying to make use of, because that will allow us to do, for example, theorem proving for molecules.
Right. And that's great at that level there. But the second use here of an exact instance of a molecule would be something more that would be useful for like Wolfram alpha. It would be a result there where you're looking for something particular, and you would have lots of data about the particular reaction. That's what's Jason has in the second use case here.
Okay, so what we've got is these name reaction type things, which are template-ish reactions. We've got specific instances of those reactions. And then I do love the fact that you've got a proposed thing called reaction apply. I mean, if these things aren't transformation rules, I don't know what is.
They are.
So that, I mean, the example there is where I define the pattern. I mean, that's a more complicated one, but that's where you define the reaction of one amino acid joining another one and making a peptide. And then you apply it to a list of molecules and get back a list.
Okay, so hold on. I'm so confused here. All right, so this is saying this amino acid, how are we labeling the atoms? I mean, so again, and maybe I'm just, again, very confused about basic ideas of chemistry. So we got a carbon atom. It's on the left-hand side of a reaction. Let's say we have a molybdenum atom, a unique molybdenum atom sitting on the left-hand side of a reaction. Eventually, that's going to wind up, somewhere in the structure on the right-hand side. Great. We can kind of trace that molybdenum atom. Now let's say we have 2 molybdenum atoms. Can we label, are we in the way that, at the level that people describe chemical reactions, do you label those molybdenum atoms or not?
They are, and the example right here shows that that's what the colon followed by an integer is. It's the mapping from the reactants on the left-hand side to the products on the right-hand side.
And why can you always do that in the world of quantum mechanics? In other words, well, particularly with one of those resonance structure things or something else, I mean, is it always the case that you can just trace, there's where the atom went?
So no, oftentimes you don't. Like oftentimes, like you have a real life reaction and you have an idea about the mechanism, and then allows you to rationalize what's going on. But then oftentimes people don't then go from that mechanism that they intuitively understand to writing out an actually atom mapped reaction. And so actually having a fully mapped reaction that fully makes sense is, I find, rather rare. I mean,
okay.
But
and they're
It's
often not mechanism based.
Idealization, if you will.
Yeah, it's
Like,
really
doesn't necessarily correspond to reality.
So
Yeah.
to make a reference that some of, at least, like in something like quantum field theory, particle physics, whatever, you would have, for example, you have, I don't know, 2 quarks, scattering of 2 quarks or something. You will have different Feynman diagrams that exchange them, don't exchange them, etc. And are you saying that in reactions, you can imagine the same kind of thing, that those 2 carbon atoms, there are essentially different Feynman diagrams that represent 2 different reaction mechanisms, one in which those 2 identical carbon atoms were exchanged and one in which they were not? Is that a true statement? And you don't?
I don't think so.
I think it depends on the reaction in question.
Depends.
While of course all carbon atoms are the same, the thing and the wave function is anti-symmetricized or symmetricized in the carbon atoms. Practically, they are really different ones. They don't switch.
Yeah. If they have different environments, they would certainly behave differently in a reaction.
Okay.
So when people want to study the mechanism of a reaction, they'll use isotope labeling. They'll put,
and you see they don't end up wherever there's a C. They end up just in a few places.
Okay, I understand. So this is kind of gives a lie to quantum mechanics. That is, these things are really not. It's as if that when you say they have an environment, it's as if they're sort of being measured somehow.
They
and
are.
That means
they are measured by the electrons and by the radiation field. That is exactly what stabilizes them.
I mean, how many protons and neutrons and electrons do you need to be macroscopic, I guess?
Well, no, but that's not what's happening. I mean, there's this notion. Okay, naive physics question here. The quantum Zeno effect, when you have continual measurement, is that effectively what happens in these chemistry situations, or what?
I think that's not unrelated, indeed.
So that's why you can maintain the identity of a carbon atom, is because you're sort of quantum Zenoing it all the time.
I've not heard this concrete formulation, but I believe this is correct, yes. I think this goes back to Armand Pfeiffer in the late 80s in ETH.
Interesting. Okay. I want to measure this quantum Zeno effect because I think it'll allow us to measure a bunch of parameters in our model of physics. But I wonder if it's been measured in chemistry. In any case, okay.
So one thing that's really going to be that we found is it's kind of troubling or not troubling. It's onerous to enter in these reactions with all of the atom mapping. And so in the next version, extending molecule draw to allow in manual atom labeling, where you just like so some type of automatic labeling saying, hey, there's only one molybdenum atom on each side, so we're just going to map those to each other. But here are the ones we haven't mapped yet. Here's a graphic where you can click, 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 click. Tools like that perhaps would be a function repository or perhaps in the system.
Okay, hold on. So but the fundamental idea here is we have a chemical reaction which has either mapped or unmapped atoms in its left-hand side and right-hand side. We have some combination of molecules with multiplicity, perhaps, that is mapped into some other combination of molecules, also perhaps with multiplicity. Is that a fair statement? And each of these collections of atoms, I mean, at a purely sort of formal level, these are sets. In other words, it doesn't matter. In a chemical reaction, A plus B is the same as B plus A, correct?
So in an actual chemical reaction, it is. As to whether or not like reaction apply enforces ordering or not, that's something that we have has been a subject of.
Well, you see, but this is like subset replace. I mean, basically what you're saying is the chemical, if you've got a whole bunch of chemicals and they're floating around and you have a reaction that's available that lets you, add chemical A to chemical B, it's as if you were doing a subset replace on the collection of all possible chemicals with just picking out those two particular ones where they can be combined. And it's a little tricky thinking about the multiplicity in the subset replace. I mean, essentially that's what you're doing, I think, with reaction apply. You've got, look, in the end, you're going to have a whole vat of chemicals, and some of them will react and some of them won't. And that's what reaction apply, presumably reaction apply could have a bystander molecule sitting there that isn't involved in the reaction, and it would just affect the molecules that are actually undergoing the reaction. Is that true?
It's not set up that way at the moment, but you could envision it that way.
Right,
it seems a little wasteful, though, to be throwing in additional elements to the reaction list that don't participate.
I know, but what I'm trying to get at is, I'm telling you, there is a more principled way to think about this, which is what these people who've been doing category theory and graph rewriting with these things and so on have been getting at. And I think that we need to, I mean, you are okay. What exactly is it that you would like to introduce right now? You've got these two. Which one is the one you care most about of these? I mean, the template reaction thing is the name reaction, as its name suggests. It's a thing which has not specific kinds of atoms, but templated structures, correct?
Yep.
Yeah, so I find template reaction to be a lot more fun. Chemical reaction is very important for the
education
Alpha Notebook.
And weighing efforts.
Yeah, for education
Yeah.
market.
And what you do with it is mostly stoichiometry. Is that true? Or mostly just lookup of a reaction?
Well, so you balance
Balancing
it. Finding the limiting reagent when they give grams
Absolute
of this
amounts.
that.
Yeah.
thermochemistry.
Mm-hmm.
Yeah.
But so when you're saying thermochemistry, you're just looking it up. You can't compute anything about that. Is that true?
Right. In general, we would
No,
call
you can do
thermodynamic
Hess's
data.
law to compute it.
Oh, okay.
But we're not there yet.
Well, so I mean, the thought would be.
How
to
do
look
you
at-
compute it roughly? Just using free energy things, something, or what?
Well, if you have a new reaction that you don't have the delta H for, the enthalpy for a reaction, and you have smaller reactions that you do, and you can add them together to get the new reaction, you do that. You just add them together with the multiple, necessary coefficients to end up your total thing, because enthalpy is a state function.
I understand that, but I mean, is that? But it's not a state function. It's like pieces of molecules can separately interact, and it just adds in that case, does it? Or does it? I don't think it does in that case. I think it would if the molecules were separate. Anyway, okay, fair enough. Yeah. But so there are, okay. So now, gosh. Oh my gosh, you really going to use a plus sign there?
So it doesn't have to. I mean, obviously, we don't have to. We wouldn't even have to use that in as.
No, but
example,
this is a good question. Is there an algebra of chemistry like this? Does it actually work? Right? If it's 3 hydrogens and 3 times hydrogen plus 2 times oxygen.
If the reaction is balanced, it works. But a lot of times people are sloppy and they don't balance.
Well, I understand that, but the concept of taking an algebraic formula and adding in coefficients into that algebraic formula is not something completely crazy from an algebraic formula.
No, it's not crazy.
So in other words, you're proposing that we really could have something where an algebraic-like variable is a chemical. Because that's what you're effectively saying here, is that's what we're doing.
Yes.
Wow.
Your point's taken, but you must be very rigorous if you're going to do that.
Because, well, but I mean, you could have something where you just type it in as, look, we could have something where it's x plus y plus z, and then we can have a function that, to achieve, I don't know, let's say you're making symmetric polynomials or something, you could just type in the monomials, and then you could have a function that goes and scatters coefficients in there. That's a perfectly reasonable pseudo-algebraic kind of function, if you see what I mean.
Mm-hmm.
What do the boy, okay.
So I must admit, I did not realize what kind of can of worms I was opening by allowing plus. I mean, I just thought it would be a convenience that the user could type plus or.
Well, but that's the point. You say hydrogen plus hydrogen, you get 2 times hydrogen. I mean, we have there is an algebra for, and it might work. Okay, it might work. The only thing is that I think, okay, here's where it will get really, really funky. Okay, let's take that object there, and this is the point. Is it's a linear algebra, so to speak. It can't be. You cannot possibly do this. This is bonkers, right?
Oh no, certainly not.
Yeah, I'm going to get hydrogen squared.
Yeah. But the real potential problem with the plus is what was mentioned earlier on the side is if we have the application, do we expect the molecules that we apply it to come into order or not? Because plus might reorder and you might not be aware of it.
Plus will reorder.
Yeah.
Yeah. Sometimes it will just keep it if it's already ordered.
Right, but you see, this is where you get back to that horror of that chemical formula thing you had before, where you're getting multiplicities with sublists, right? So the alternative would be you can represent these things as list blah blah blah, arrow list blah blah blah. But now, and this is why I knew my little antennae were wiggling, and when we were talking about chemical formula, that something was going to go wrong, because you're going to want to put the multiplicity. You're going to want to add multiplicities here. Right.
Oh, absolutely. If
I know, and then you're going to want to use something like the chemical formula multiplicity thing, at which point you've got an ugly data structure that's hard to deal with.
Well, so if you scroll down, there's a reaction under, right? So there, I mean, where it has the factors out. So so that's one of our examples in alpha that Jason found that it's a rather difficult one to balance.
Correct.
That's a serious set of Diophantine equations.
Even I don't see your potential problem. Can you repeat?
Okay, so what I'm saying is, you're saying, let's use chemical formula-like syntax to represent these chemical reactions, which means that when you're representing multiplicities, you're doing this kind of hacky thing of saying blah, list blah, comma 2. Right.
So in the canon, so if you did the full form of that one directly above the cursor, it does end up, I believe, using lists for multiplicity.
Right. I mean, so if that thing, input form of that thing, oh my gosh, no, you can't do that. Look, now the multiplicity is before the chemical formula.
Well, because you write it that way.
Well, entertaining.
By convention.
Yes, but this is not a computable thing. I mean, that 10 is as much like your paren 3 as anything, right? That 10 is really this chemical thingy paren 10, isn't it?
It's 10
molecules,
copies of that molecule, whereas the subscript ones are 10 copies of those atoms or collections of atoms that are submolecular.
Groups,
that's the chemistry convention from the past 200 years.
I'm aware. Yes, I'm aware.
And
but
maybe that could very well not be computable in today's modern languages.
Well, so
but anyway, like if we don't want people to go in, take this apart. We want to supply sub-values to do things.
That's my thought. That I mean,
you're saying this is opaque.
Yeah.
So this thing.
People could do this, but why would you do it?
But how do you look? If you simply want to enter that chemical, this thing here, how would you enter this? With a string or what? How would you
So-
enter that formula?
So I don't know how to make interactive boxes, that kind of thing. So you mean like put your cursor in there and
The
start
vain
typing?
template like input might be very convenient here indeed.
Sure, I'm just saying if we wanted to make this, I mean, by the way, I have all kinds of interesting comments on our live stream, and I hope somebody's going to make sure to store these and send them out to people, please. Language for biochemical systems. Okay, there's a whole, yeah, right. I've seen a bunch of these. These are things about, can you machine learn what reactions happen? And yes, that is interesting, although a little bit different from what we're dealing with here. But this, what is this language for biochemical systems? I don't know that, although it may be related to a bunch of these yeah, well, okay. Okay, yes. I think there's a grand unification here of, all this graph rewriting, multi-way graphs, all this stuff with chemical reactions. And I know you guys are keen to get sort of practical things that deal with the simple cases in there, and perhaps we can do that as experimental functions. I do think that there's a really nice unification that can be gotten, and I think that the more we burn in, well, okay.
So the full form of that reaction there, it could easily just be an association, as opposed to the chemical formula where you need to maintain the hierarchy that the user put in. So there's no reason that the canonical form of chemical reaction here couldn't be an association with the counts
right.
as the right-hand side.
You can always make it atomic. Now we can look in and move.
That's.
Well, I mean, I can only make it the fake kind of atomic, which if you know how to, you can look inside.
Well, okay. We're running out of time. We all need to continue this, as you expected. Oh boy.
But I mean, the general idea of two different data structures for this.
Why isn't it just pattern variables in the chemical reaction?
So you could make, so that would be the other alternative, would be to have one object. It would be chemical reaction, and if it had molecule patterns in the as the reactants and products, then reaction apply would work. If you didn't have molecule patterns and had regular molecules and entities, then reaction balance would work. And so that's the thing, that I could make them one unified thing, but then I would have to have these internal switches that are always saying, are you a template reaction? Okay, then do this. Are you not? Then do that.
And they would also behave different, yeah.
Right. I mean, in a template reaction, you would never put a stoichiometric coefficient in front of something, because you want to literally map every atom.
Right.
Yeah, you have to do it that way. Even if you have two copies of one molecule being involved, for example, in the dimerization, they still need to be present individually.
Okay. No, I mean, I do understand why it's useful to have two different things. Give me an analogy, though. I mean, in one case, what are these like? The difference between, go ahead.
Well, so I mean, it seems very much like a string to a string template.
Yeah, that was what I was going to
Yes,
suggest
okay.
too.
But notice that we're doing that with pattern variables.
Right. I mean, the structure of the template.
It's considerably simpler. It's a linear, it's a one-dimensional object rather than these graphs.
Mm-hmm.
Jason, do you mean string template or string expression?
He means string expression.
Okay.
Okay, Richard on live stream is mentioning BioNetGen, which apparently compiles. Well, I think that is probably similar to what System Modeler is doing. And by the way, does anybody know, when we're dealing with chemical reactions, does anybody know how this relates to what's been done in System Modeler with chemical reactions? That's a big silence.
I'm only familiar with the high school laboratories that they built. One is modeling a chemical reaction, but that's just a couple of
Right, they have much
equations.
fancier things that are used by pharma companies and so on.
Right, and a lot of that is, I mean, it's concerned with the kinetics of reactions, right? That
well, it's concerned in the end with making ODEs that represent, you know, this concentration, that concentration, this rate constant.
Right. Yeah.
Chemical kinetics, yes.
That's kinetics.
Right. Okay.
Which is not this stuff.
Okay,
right,
but how do we go from this representation of a chemical reaction to saying, okay, this has rate constant blah, and now I'm going to have this list of chemical reactions, give me the whole sort of story of the, you know, the reaction network and its ODEs and so on?
Well, so I have it tentative at the moment, but some of the parameters in this, the association that you could give would be things that we can't necessarily compute, but that could be used later on down the line, like a reaction rate.
Yeah, my compartmental modeling package could handle that, Stephen. It would basically take something that looks very much like A plus B goes to C plus D. And A and B would be two molecules, and C and D would be two other molecules, and it'd be a rate constant. And you can generate the differential equation. You can have several reactions in your system, and it'll generate the ODEs for the coupled system.
Right. Boy, and that is just like a token event graph in our other world. Fancy that. That's like the mean field theory of token event graphs. Okay, fascinating.
Well, everything boils down to zeros and ones, doesn't it?
Yeah, but going through graphs and graph rewriting, it seems. Okay, there was another comment here. Let's see. Just look at these other comments from Kay here. Right. Yeah, right. I mean, this is about what molecules are and so on.
There's a webinar which is touching on this. What molecules are?
What was this?
You mean at the philosophical level?
No, on our what the molecule is in the language. It's a webinar upcoming. If people are interested, we have still some seats available.
Okay.
No hidden advertisement in this meeting, to be honest.
Okay, sorry.
Let's see. Richard is making a comment here about, yeah, I mean, this whole business about, okay, there's also the relation of these things to Petri nets. That's another whole story, which I think I'm finally understanding. Anybody else here understand that?
Yes, I've used that structure for modeling the chemical kinetics.
But without rate constants, right? Petri nets are just the combinatorics of what's going on.
Yes. Well, perhaps I'm using a somewhat perverted I call them Petri nets because you've got a set of nodes that are the reactants and products, and you've got another set of nodes that are the reactions that are between them. And it's a bipartite graph, and it's very easy to trace stuff out. And the reaction rates are actually held in the reaction nodes. Yeah, right. And it's a directed graph. And it's a very convenient way to represent it. I know Petri nets are also used for modeling information.
Well, right. I just posted this thing just today about this whole multi-computation business.
Yeah.
In which Petri nets come out as a token deduplication of these token event graphs, which are token event graph is like the individual molecules interacting with reactions. And if you conflate all copies of a molecule together, you end up getting a sort of Petri net representation of those things.
Yep, that would be it. Yeah, taking everything that's in the beaker, as it were.
Right. Oh, okay. We're being pointed to a thing called Cantera, which I've never heard of. Anybody heard of that?
No.
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 Tools. Well, we should look at it. Thanks for that pointer. This is chemical kinetics stuff, it looks like. Cool. All right. I unfortunately have to go, and oh, okay. Yeah, I mean, look, this is a highly interesting subject, and one that I think we should try and solve at a kind of a little bit higher intellectual plane than just, the particular kinds of things that are needed for sort of educational chemistry, so to speak. But we obviously need the educational chemistry stuff in there. And I think the general direction, Jason, that you were, look, it seems fine for this level. And by the way, I don't know which of you, we are having, I think, our kickoff meeting about this whole multi-computation framework tomorrow. Maybe at least some representatives of the chemistry world should be there. And I think we'll live stream that so people can check that out. All right, we should wrap up here. Thanks a lot, everybody. Very interesting stuff. Thank you to folks on the live stream. Lots of very good comments, much appreciated.